All right, everybody. I got just after 1 by my clock, and thank you for joining us on our Science Saturday presentation. I think this is the 3rd or 4th one we've done, and we're going to continue doing this to kind of keep everybody updated with some of the things we do in the Weather Service offices, how we incorporate the science of meteorology, and keeping everybody at home safe and producing forecasts. So, I'm a meteorologist here at the National Weather Service office in Shreveport. My name is Brad Bryant, and I've been forecasting this region for a long time. And one of the things I know as a meteorologist that really benefits what I do is the weather radar. So that's what we're going to be talking about today, is an introduction to weather radar interpretation. We're going to be talking a bit about the science on how it works, and talk about what kind of information the weather radar delivers to us, and how, as you at home, can use that information, and a little bit about how us as meteorologists, how we dig into the details of that information to help bring you warnings and issue tornado warnings, severe thunderstorm warnings, and to help fulfill our mission of protecting life and property. So first, with radar, talking about radar basics, it is an acronym, meaning that every letter of radar stands for another word. So what it stands for is radio, detection, and ranging. Now, radar has been around for a long time. I guess it was started to be used in World War II, and it was developed initially before that, so nearly 100 years. But back in the 40s and 50s is when it really started to be used for weather detection. And starting in the late 80s into the 90s with the next-rad radars is when the radars really got good. And that is information, the kind of information it gives us now about precipitation is what people are kind of used to seeing. And that started back around 1990. And even though a lot of the weather radars that we use in the Weather Service, they're still kind of based back in the next-rad implementation. There have been improvements, gradual improvements, to make that data more resolute and sharper and crisper and come in more frequently. And I'll talk a little bit about that as we go along. So radar is electromagnetic waves are emitted from a transmitter, and like in this graphic you see, this electromagnetic energy will kind of go out and then hit droplets in the air, and usually that's water droplets, and the information will come back and give the radar an idea about how much water is out there and where it is. So the way our weather radar works, everybody is probably used to looking at one level of weather radar. When you watch the weatherman on TV, he usually shows what is called a base elevation, which is the lowest slice of the radar, kind of just above the horizon. But there's multiple levels in a volume coverage pattern, which kind of gives a 3D picture of what's going on in storms and in areas of precipitation. And meteorologists particularly like to use this 3D picture to get a good sense of how a storm's developing or its severity. And there's different volume coverage patterns that are used in different varieties of weather scenarios. So this is just an idea of way the weather radar shoots. So generally, you have your lowest slice there, and that's what is shown on TV, and like when you use your weather radar apps, that's usually the information that it shows is from the lowest slice. And when you're looking lower towards the ground, that information that the radar is delivering about precipitation has the most tie into what you're experiencing at the surface. But as the radar shoots higher and higher, you get some picture of what's going on with the higher levels of a storm. And it fills out that 3D picture of storm growth and whatnot. So some limitations of the weather radar that meteorologists really have to deal with is the beam height increases. So the radar shoots out above the horizon, and as you go away from the weather radar, we can't shoot directly out from the horizon because the beam will hit too many things. It'll hit trees, it'll hit buildings, and it'll give you a lot of bad data. It won't be reflecting off of water droplets. It'll be reflecting off of trees and building material, and we don't want that. So it has to shoot a little bit above horizontal. But when you do that, when you start getting well away from the radar, say 100 miles, 150 miles, that radar beam is many thousands of feet above the surface. And it usually starts out only a couple hundred feet above the surface. And when that radar beam is many thousands of feet above the surface, then what it's telling you about what's going on in the atmosphere has a little less correlation with what's actually going on down at the surface. So you like for that radar to be as close as possible. And also another thing that impacts that is the curvature of the Earth. Because when you're dealing with 100 and 150 miles, the Earth is round and it curves, the surface of the Earth curves, so that beam is going to be pulling away from that curvature plane as it goes, and which is also going to increase the height above the ground as you get further out. And there's also an aspect of the beam kind of goes out in a sort of a conical pattern, and it gets wider and it spreads out the further away from the radar you go. So it doesn't, when it hits reflectors, like less energy is scattered back to the radar, and you get a less detailed picture when you get well away from the radar. So those are some limitations. There's a few more too. You really want to know your location, where your radar is with respect to the weather that you're looking at. Like, and this is a case where a radar is up in central Illinois, and it's looking over 200 miles away at storms in southeast Missouri. And that's really too far away for meteorologists to be doing a close examination of storms. Because in that instance, that weather radar is just seeing the very tippy tops of those storms. Now, if you look at this radar over here in Paducah, it's only, about 100 miles away, and it's looking at the same storms at the same time, but you see a lot more going on. That's because it's looking at the mid and upper levels and giving you a lot clearer picture of what's going on actually at the ground. So you can kind of see in this graphic where you have different radars located across the country, and they're going to, maybe there's a particular storm cluster, and they're going to sample it differently. And you really want to sample more the lower end of the storms, lower down towards the ground, not the higher end, to get a true picture of what's going on at the surface. Now, fortunately, there's tools that mosaic radar images from all across the country, and on a lot of Weather Service radar pages, it'll give you this pretty mosaic that kind of folds in all these pictures from a bunch of weather radars looking inside of 150 miles from all the weather radars. So it gives you a clearer picture. So you're not sampling anything from radars that are at an extreme distance. All right, another limitation of radar is, like in Shreveport, our radar is in Shreveport, right here at the office, and right around where that weather radar is, the weather radar tends to pick up a lot of things that aren't necessarily weather. Most of the time it's going to pick up ground clutter, because there's a little portion of that beam that's going to reflect off of trees that are high trees that are close to the radar, and it'll reflect off of birds, bugs. Sometimes in this image you can see a smoke plume from a fire that'll show up. So we always have to keep that in mind. Right around the weather radar, maybe within 30 miles, there's always going to be a little bit of light echoes that show up that generally aren't weather. Another thing to keep in mind is a lot of times in the mornings, especially on maybe not summertime mornings when it's warm and humid, but maybe crisp, cool fall mornings when the wind's real light and there's a lot of radiation or cooling, you tend to get inversions set up. And when inversions set up, it's where the temperature decreases a whole lot towards the ground in the lowest maybe 1,000 feet of the atmosphere. And that inversion tends to duct the radar beam down to the surface. So instead of going above the horizon, that radar beam, when it hits the inversion, will duck down towards the surface, and you end up with this pattern where you got a lot of light reflectivity echoes that are all over the region. and it's because of this ducting when inversions set up near the ground. So we're going to talk a bit about different products that the radar gives us. There are 6 base radar products that the radar delivers to us that meteorologists are really interested in. But there's also a whole bunch of derived products that go out through the Weather Service and out to the public. And a lot of these derived products are based on the base products, and these are things like rainfall estimates, hail size estimates, rotational tracking, and there's a whole lot that people make use of to help monitor severe weather. But when you're really interested in getting into the nitty-gritty of exactly what's going on, a lot of times the base products are what you need to look at, and that's what meteorologists, we like to focus on when we're issuing warnings. So I've already talked about base reflectivity, and that base reflectivity is generally the lowest slice from the radar, closest to the horizon, that's going to look as low as we can in the atmosphere. And that is measuring the energy scattered back toward the radar. And that's where generally you see greens with light precipitation, yellows with moderate precipitation, reds associated with heavy precipitation. And that the values we get back are in terms of decibels of reflectivity called dBZs. So some of the dBZs you can see on the radar are very light. Sometimes they're negative or close to 0. And really heavy dBZs can be up over 80. And I've got here around 90 for a peak, but I never really seen 90 myself. Another way to look at the radar is through composite reflectivity. And a lot of your weather radar apps may have that option to look at composite reflectivity. And it helps out a lot if you're very near a radar. Because sometimes if you're really close to a radar, that lowest slice, that base reflectivity slice, can be shooting underneath a storm that's maybe located up here. And if you want to get a sense of where that storm is and how strong it is and how much rain is in it, you might have to use a composite reflectivity slice, which essentially will tell us what the highest reflectivity is at any level using the 3D radar picture we get from the whole volume coverage pattern. It'll show the highest reflectivity at any level over a particular location. So this is an idea of the difference between base and composite reflectivity. On the left is what a supercell thunderstorm would look like a typical hook echo in a supercell thunderstorm using base reflectivity. It's very good about showing us the shape and the structure of a storm, but if we were to look at it in a composite reflectivity sense, we would be sampling all these higher returns that are above the really good structure, and it's sort of, in this case, it would not be good looking at composite reflectivity, because meteorologists, we really want to hone in on the hook with the storm and on where the tornado could be, and we don't want to have it messed up with all this other reflectivity in the composite reflectivity sense. But in some situations, like I said, when you're really close to the radar, it is good to look at composite reflectivity to get a sense of what the base reflectivity might be missing. So another product, a base product that comes out of the radar is velocity. Reflectivity is just half of the picture, and especially when we're worried about severe weather, we are very interested in velocity. And velocity relies on the Doppler effect. And the Doppler effect keeps track of not just the reflected energy, but also characteristics of that energy, like its shape, position, and form. And so by measuring the energy that comes out of the radar has a specific phase. And when it hits it reflects off a target, it'll come back with different phase information depending on how that target is moving. And the Doppler shift of that wave coming back to us gives us a sense of the winds, because if that water particle is moving away from us really quickly, it'll show up in that phase shift, or vice versa if it's moving towards us. So here's a Doppler effect, a train example, and hopefully you can hear this okay. But as you hear the train get closer to you, the sound increases in frequency a great deal and increases in pitch. And as it goes away from you, it drops in pitch. Now, this is using just sound waves and not electromagnetic waves, but it's the same sort of principle as what goes on in the Doppler effect and how the radar figures out the speed of objects and if they're moving towards or away from the radar. How this runs through that Doppler train effect again. Okay, so one base product, base velocity. Once again, if we're talking about base, we're just looking as low as we can in the atmosphere, and it's measured in knots. And some people might be confused about knots, but a knot is just a little more than a mile an hour. It's maybe like 1.1 miles an hour. A lot of things in meteorology use knots. So we use it to determine the wind speeds by measuring how fast reflected targets are moving toward and away from the radar, and generally it depends on the way you have the radar you're looking at, the way it's tuned, but generally it's the case that red will be associated with targets moving away from the radar and green will be associated with targets moving toward the radar. This is output from base velocity, and the radar is kind of down here where my finger is pointing, and it's looking, of course, up to the northeast, and there's a supercell thunderstorm right here, and we can't see it because we're not looking at reflectivity. We can't see what we traditionally might see, but we're just looking at velocity. And if we were to see this associated with a supercell thunderstorm, it shows right next to each other, side by side, a lot of reds, strong outbounds, and greens, strong inbounds. And that is suggesting rotation. And if anybody lives around, the South and in lower Mississippi Valley, Tornado Alley, they know about reds and greens being close to each other in rotation, and a lot of times that can indicate a tornado. And so as meteorologists, we really track these rotations, and if they get to a certain strength, we might issue a tornado warning. So one of the things we really have to keep in mind as meteorologists when we look at velocity, and this can be a little tricky, and it involves some trigonometry at times for y'all that have been through trigonometry, but the radar can only fully measure the velocity for things moving directly at or away from the radar. So in these situations, like number 8 there and number 4, like in this situation, if the wind is coming up from the south, like those objects will be moving directly perpendicular to the radar beam, and you would not get a sense of how fast they are moving. The velocity that would show up for those objects would be 0. Now, an example of how this works out is, okay, this is a situation we're looking at velocity associated with a storm moving to the north. And in this scenario, this radar is down here to the south-southwest, well actually more west-southwest, and it's looking off to the east of this storm. And because it's moving, most of that movement is more perpendicular to the radar beam, then it's not sampling it very well. So it's only sampling 30 to 40 miles an hour of wind. And if a meteorologist is making a decision looking at that, they would say, well, that's not that strong. We don't need a severe thunderstorm warning. And our severe thunderstorm warning is generally 58 miles an hour. That is our threshold. So at the same time, there's another radar that's closer, that's up to the north. And this storm and its wind is moving directly at that radar. So we're fully sampling that storm's wind. And we're seeing there, measuring winds of 70 to 75 miles per hour, getting a true sense of what that wind is in the atmosphere. So the warner, they might issue on this. And in this case, this was a severe thunderstorm. So another sense about velocity, a lot of times if you look at the base velocity and you're in one of those wintertime systems that has a lot of wind wrapped up in it, and we're looking at velocity patterns associated with the line of storms, we may see nothing but, like over here, nothing but reds, all kind of outbounds. But within that, there is circulation. Even though you don't see greens, there is circulation. And for that circulation to show up better, you can do something called use storm relative velocity. So it will take the velocity of the system, the movement of that line, and subtract it away from the ins and outbounds you're seeing from the radar, and it'll give you a better sense of the rotation then. So another aspect of radar that's pretty new, it started in about 2013, we started using it here, is dual polarization. And it can get pretty tricky kind of to describe the science and physics of it and how it works. But simply, before dual polarization, the electromagnetic waves that came out of our radar were oriented more horizontally, okay? Vertically. And now with dual polarization, we're sending out a horizontally oriented pulse, and vertically oriented pulse and a horizontally oriented pulse. And depending on how much energy gets reflected back from a scatterer with the horizontal and vertically oriented pulse, you can get a sense of the shape of the target you're hitting. And you may wonder, well, who cares about that? But it does give us a lot of information about the weather that's going on. So correlation coefficient is a product that we can look at that really makes use of this dual polarization technology. So it can tell us the different shapes of the targets we're hitting, and a lot of times these shapes can suggest whether it's rain or snow, whether we're actually hitting birds and animals and bugs or bats or actual weather. Or in some cases, and this is where it can be really helpful for us down here, where we don't get a lot of winter weather, but we do get a lot of severe weather. When you get tornadoes going on, those tornadoes can loft debris, and they can give us a signal that says, hey, look, that's not weather that we're picking up at all. That is pieces of trees, pieces of houses that have been lofted up in the air by tornadoes. And it can give meteorologists high confidence that a tornado is on the ground. And that has been a really critical thing in the last 10 years to try to incorporate what's called a tornado debris signature to give us confidence that a tornado is happening, even though we haven't got any reports back that anybody's seen it yet. So this is a case where the correlation coefficient can show us, because of the different colors here, when the correlation coefficient gets lower than 100% and lower than 90%, then you get a mix of returns in there. And in this sort of situation, it might be rain turning over to sleet or snow. But what I was talking about in a severe weather sense is detecting a tornadic debris signature. And so here's a hook echo, and at the base of a hook, you have your strong inbounds and outbounds right there. And panel number 3 down here, you have really low correlation coefficient. And meteorologists spend a lot of time trying to figure out how to actually call something a tornadic debris signature, because it's not as easy as just seeing really low correlation coefficients. They have to be lined up properly with rotation, and there has to be underlying rainfall happening at the same time. But once we can make that call, then we can go out and message warnings with high confidence of tornadoes. All right, so now we're going to talk about some radar signatures. I'm going to kind of go through some of this real fast. One that's been around for a long time, but it's pretty neat to talk about, is a hail spike. And we can often see this with strong thunderstorms that have hail inside of them. Sometimes in the summer, that hail doesn't get down to the ground because it melts. But in this situation, the weather radar is up to the north, and it's shooting into this core of this storm, and it's having this little spike come out of this high reflectivity core where there's some hail. And what is actually happening is neat. The weather radar, it's sending out this signal. It hits this core of hail and rain, and that bounces some of the energy back to the ground, which then reflects off the wet ground and back up into the hail spike, and then a little piece of that energy finally, through that circuitous route, comes back to the radar, and it gives this little trace of, there's not actually weather going on right there. That's just an artifact of all the electromagnetic waves bouncing around. Kind of neat. So I'm going to talk about different types of storms we can see in our region and how the radar helps us identify those. In the summer, we often see pulse thunderstorms, and I'm not going to get into the details of wind shear and instability, but in the summer, we usually don't have a lot of wind shear, and we have a lot of instability. And that drives storms that tends to go just sort of like straight up and straight down and aren't highly organized. And sometimes they can produce these interesting rings of outflow when they come up and down and collapse, and they just, the wind from them goes out in all directions and makes this really interesting kind of outward circular appearance. And you can get severe weather from pulse storms. When the storms, their downbursts, when they initially collapse, they can produce some very localized wind damage. But the storms that produce damage more often have wind shear associated in their environments, and they get organized. And the first level of that is multi-cell storms, and they have enough wind shear to organize loosely into clusters, and sometimes in the summer we get enough wind shear where they kind of loosely organize into these clusters, and they may last a little longer than pulse thunderstorms. Here's an example of what we get a lot in the summer, where we have a lot of southerly flow, and thunderstorms kind of organize on that southerly flow throughout the afternoon and kind of race north through the four-state region and can produce some gusty winds along that outflow that races north. So one that we see a lot over the cool season from fall through spring is squall lines. And and those can produce widespread organized wind damage and embedded tornadoes as well. We saw a big one of these. This is from January 10th of this year, where we saw widespread wind damage that got going in East Texas, went through our region, all the way through the southeast, and there was embedded tornadoes all over the place. And one interesting thing, this is from last October, this is a squall line, and when you see these kinks in the squall line, like right in there, is where meteorologists, we look for maybe embedded tornadoes spinning up. And I'm going to zoom in a little bit on that kink, and in the bottom right you can see there's a little drop in correlation coefficient, and it may be hard to see the detail of this, but that's actually a tornadic debris signature. And what's really interesting, when we issue tornado warnings and we get damage, we'll go out the next day or 2 days later and we'll do damage surveys. And we did a damage survey, and the tract of the tornado we surveyed was right along where that tornadic debris signature is. So you can see how helpful having that tornadic debris signature in our toolbox is for doing surveys and for getting warnings out and letting people know, look, there's a tornado, and we know it's on the ground and it's coming. All right, so supercells are the big ones that generally can be capable of the worst significant severe weather. It can sometimes be 50,000 feet tall. You need, most of the cases, you need high instability and high wind shear. A lot of violent tornadoes, the majority of them are produced by supercells. So what a supercell looks like, we've already talked about it. It's got a hook echo. Sometimes in the hook you'll get high reflectivity if there's debris in there, and associated with that is that high rotation. And this is an image from a huge tornado outbreak in Oklahoma in May 3rd, 1999. And I wanted to point out one aspect of supercells in here. And at the beginning of the loop, as these supercells start going, you can see them start to turn to the right. So they'll kind of start off going this direction, and then all of a sudden they'll sort of, and it's hard to point with, but yeah, they'll turn off to the right, like more eastward. And that's an interesting facet of supercells. When they get organized, generally they'll turn off to the right, they'll deviate from the mean wind. Now, those are classic supercells from the plains. We're not really in the plains, we're more towards the lower Mississippi Valley where there's a lot more moisture, and we more deal with high precipitation supercells, and those kind of tend to look messier and are a little less classic and sometimes harder to identify. This is one case in Mississippi where you have a bunch of blobs on the reflectivity on the left that don't look particularly concerning until you look at the velocity patterns where you have really tight rotation, really tight outbounds and inbounds. And in particular, this one cell went on to produce a violent tornado that went across Hattiesburg, Mississippi. So in this part of the country, when you don't have supercells that are classic all the time, you really have to look at velocity really closely. So that's all I got, and I'll kind of open it up to questions. I'm relatively new to Facebook Live, so I'm going to check and see if there are any questions here. I don't think I'm seeing any. I know I've had some people that are outside of here maybe answering some questions as we went along. But Yeah, I really appreciate everybody tuning in. You know, this is our weather radar right here at our office in Shreveport, Louisiana, and this is a really nice picture that one of our meteorologists took of a thunderstorm complex, kind of backlit at sunset behind the weather radar. And if you have any questions that you want to ask us that maybe that come to you later and not right now, feel free to shoot us an email at right down there, sr-shv.webmaster@noaa.gov, and we will get to them as quick as we can. And I might hang on here a few more minutes